Good day, students. Today, we shall look into a new chapter, Basic Elements of Spectroscopy. In this, we shall look into what is a spectrum, what do you mean by spectroscopy, what are the different regions of the electromagnetic spectrum, what is a grating spectrometer, and how do you record a spectrum. Now, spectroscopy can be defined as the study of the interaction between matter and electromagnetic waves. If we want to know about a particular compound, a particular metal, a particular material, we usually radiate it with light or X-rays or microwaves or radio waves, and we study the emerging electromagnetic waves from it. So there will be an interaction between the matter and the waves, and we study what that interaction is. This study is called spectroscopy. Now the spectroscopic data, it is represented by using a spectrum. And what is a spectrum? It is a plot of the response of interest as a function of wavelength. By spectrum, we understand that it is a plot or it is a graphical representation. On the x-axis, we can have the wavelengths of the electromagnetic spectrum, and on the y-axis, we shall record the response that we want to record, the type of response that we are interested in. If we want to record the amplitude of the transmitted light, we should record transmittance on the y-axis. If we want to record the absorbed light, the amplitude of the absorbed light, we will record the absorbance on the y-axis. Okay. So here is shown the picture of a spectrum. We see different colors, right? So this is a spectrum of the white light. It contains different components of light ranging from violet to red. So this is also a spectrum. Now, this is the graphical representation of the spectral components with the wavelength in the x-axis and the percentage of relative energy on the y-axis. So in this spectrum itself, we can see that even though there are different wavelengths, the amplitudes of the different wavelengths are different. The amplitudes of the violet spectrum, blue spectrum are smaller, whereas the amplitude of the green spectrum and the yellow spectrum is the highest. Now, even in that spectral region, if I confine my spectrum only to the violet region, if I study the wavelengths only in the violet region, I can see that in the violet region ranging from 380 to 410 nanometers, again, we have particular wavelengths of different amplitudes. If you remember in mercury arc spectrum, if you would have noticed in the first order spectrum itself, we will see two violet lines, one very faint line and one a bit more brighter line. So there are different spectral lines, different spectral wavelengths in violet itself. It is not a continuous spectrum. We don't get all the wavelengths. Here, I can't say that we get 385 nanometer. There is no spectral line at that point. But I can say that at 395 nanometers, there is a spectral line. Now, we get data from the atmosphere, from the sky, from the different universes, from different galaxies by studying the radiation coming from them. Okay, so here I have shown you pictures of different galaxies. This is the picture of a spiral galaxy, our Milky Way. And this is the picture of a nebula constellation. It is a gaseous space in the outer space. So from these spaces, we don't get the matter itself. We get to see only the radiation coming from it. By studying the radiation from it, we understand what are the component elements or what are the component gases in those regions, in those galaxies, in those universes. Okay, again, we can study not only that macroscopic levels of universes and galaxies, nebulas, constellations, we can also study the microscopic details within matter. If you radiate the atoms or the nucleus itself with gamma rays or X-rays, that will get excited, and these excited nucleus and atoms, they de-excite to give radiation, and by studying the de-excitations we get information from that particular nucleus. Also, in the second picture, I have shown that these are the pictures of certain microspores, very small fungal growth, and they are shown in daylight and they are shown in ultraviolet light. So in daylight, its features are not that clear, whereas in ultraviolet light, we can see that these microbes are excited. They are excited under ultraviolet lights. So it is showing a response to ultraviolet light. So we say that ultraviolet light is a characteristic wavelength of that microbes. So in this picture, I have generalized that by radiating a molecule with a particular wavelength, it can show responses in different other wavelengths. Okay, so if this molecule is radiated with green light, it can show responses, it can show scattered light in red wavelength and also in blue wavelength. So depending upon each molecule, its response will be unique. So for each molecule, for each element, their responses are unique, and hence we use this type of spectroscopy to learn about each matter, each molecule, each element. Let us learn about quantization of energy. So up till now I had been saying that matter is radiated with light. Light is being radiated, or it is being shined on this matter, and matter gets excited, right? Matter does not get excited in all the wavelengths of light. It gets excited only in particular wavelengths. So earlier, during the times of classical physics, it was understood that radiation, like an oscillator, assume two molecules attached together by a string, and they can oscillate. So this oscillator can have continuous energy distribution. It is assumed as such. That is, if these two molecules were disturbed, it can oscillate in all the frequencies. It was assumed as such in classical physics. But then in 1900, Max Planck made that daring assumption. He did not have any idea about it, but still he was brave enough to say that oscillators of radiation should not have continuous distribution of possible energies. It can have only specific energies. That is, if an atom is in the ground state and it is excited by shining light upon it, it cannot randomly be excited to energy, to any space here, to any random energy level. It can be only excited to these particular energy levels, E1, E2, E3 and E4. There is a specific amount of energy that has to be absorbed so that it can be excited to the upper level. Okay. So Max Planck said that an oscillator emits radiation of energy h nu when it jumps from an energy state to the next lower energy state. So in this figure, this atom, when it jumps from this energy state to the just nearby lower energy state, it will emit radiation. This process is called emission, and the energy radiated will be equal to E equals h into nu, the frequency of that radiation. Likewise, an oscillator absorbs radiation of energy h nu when it jumps from an energy state to the next higher energy state, and this is called absorption. That is, when light is exciting an atom in the ground state to the next higher energy level, that atom will absorb energy, which is equal to E equals h nu, where nu is the frequency of that incident light. Here, emission and absorption will take place only in discrete quantities. Okay, so there is a finite amount of energy, fixed amount of energies. And that discrete quantity of energy is called a quantum of energy. And that is given by E is equal to h nu, where h is the Planck's constant. E is equal to h nu defines the quantization of energy. Now, when energy is given to a molecule, that molecule can rotate, it can vibrate, its electrons can get excited, and it can translate, move around. Okay. So just imagine a molecule. Okay, if it is excited, assume that it can move about the lattice. It can move about in a space, or else it can remain in a position and rotate along its axis, or else it can remain in a position and it can stretch or compress. In other sense, it can vibrate from a particular point. Several processes are possible, and for each process, that molecule takes up a finite amount of energy, and that energy is called its rotational energy or vibrational energy or electronic energy or translational energy. So let's see what they are. Rotational energy. It is by virtue of the bodily rotation about its center of gravity. So according to this figure, at this point of axis, this molecule will rotate along this point of axis, along this center of gravity. And that rotation will be according to the quantized rotational energy levels. The rotational energy can be of two types. In a molecule, there are different atoms, and within an atom, there are electrons and the nucleus. Electrons are surrounding the nucleus. The electrons have a particular spin, and the electron spin can change. That is, direction of rotation of the electron spin can change. That in effect produces rotational energy. Or else the nuclear spin can change. That also requires particular rotational energy. Now, when the molecule vibrates, it takes up vibrational energy. So, vibration is the periodic displacement of its atoms from their equilibrium position. So, at equilibrium, the molecules will be at a particular position, but when they are excited, it starts to vibrate, or it is displaced periodically from its equilibrium points. And due to this vibration, the molecule takes up a particular amount of energy that will be greater than the rotational energy. Okay, so it takes up vibrational energy, it will be greater than the rotational energy. So the vibrational energy levels will be far larger than the rotational energy levels. Now, molecules can also take up electronic energy, that is, the electrons surrounding the nucleus in an atom. The electrons can jump from the different shells, from the K shell to the L shell. Okay, so they can have a transfer of electrons within the orbitals, and with these transfer between the available energy levels, they emit or absorb electronic energy. Electronic energy is greater than vibrational and rotational energy. All these three are quantized energies. So there will be quantized energy levels. Now, translation energy is seen when the molecule moves freely through that space. Translation energy is not quantized. Only rotational, vibrational, and electronic energies are quantized. So in this figure is shown the electronic energy transition, and this figure shows the translation movement can move together as a whole towards the right or towards the left. It is just moving freely through the lattice. Now, the energy differences between these rotational, vibrational, and electronic energy levels are very small, because E is equal to h times nu. H is of the order of 10 raised to minus 34, right? Planck's constant is 6.626 into 10 raised to minus 34 joules second. So the energy levels will be also very closely spaced. To measure these energies, like we need to measure these radiation, right? So we will be measuring the energy of that radiation. To get a measurement, we have to take the energy in joule per gram mole. So we will calculate the energy for a molecule itself. So that value will be a bit more higher, and we can get readings from the instrument. Now the order of the energy levels, the increasing order of energy is that the smallest energy levels will be for translation energy, then it will be for nuclear spin, then it will be for electronic spin, then rotation of the molecule, then vibration of the molecule, and then electronic orbital exchange of electrons. This figure, it is clear that if this is the ground state of the electronic orbital and this is the first excited state, near the ground state of the electronic orbital itself, we get this much vibrational energy levels. All of these vibrational levels are existing nearer to this region. So they are that small. Now, in the vibrational energy levels, near the ground state of the vibrational energy levels, the rotational energy levels are existing. All these energy levels are located at this point. Okay, so the rotational energy levels are far much smaller than vibrational energy levels. So likewise. Okay. Now the transition between these energy levels from the ground state to the first excited state, or from the second excited state to the ground state, can be represented in frequency, in wavelength, or in wave numbers. So the unit for frequency will be hertz, the unit for wavelength will be meter, and the unit for wave number will be meter inverse. Wave number is 1 by lambda, so its unit is meter inverse. Generally, the energy difference is represented in wave numbers. Now let us see what is spectroscopy and how do we do it. By spectroscopy, we understand that it is the study of the component wavelengths in that light. So we are studying what are the different wavelengths and what is the amplitudes or intensities of each wavelength in that light. So in this figure shown here, I can see that we have a source light falling on the prism, and that prism separates it. It disperses the different components, different wavelengths, and those wavelengths, if that light is focused onto a screen, we can see the different component colors. So we are trying to study each component colors, different component wavelengths in that light. In emission spectroscopy, what we do is we take a sample which is excited, which is heated. Here, for example, it is shown heated hydrogen gas. So when these hydrogen molecules are excited, it will have the hydrogen atoms in different energy levels, right? So the hydrogen atoms, all of them will not be in the ground state. They are excited. So the hydrogen atoms or molecules will be located in, their energies can be represented in different specific energy levels, E1, E2, E3 and E4. Now, if this heated gas is then, its radiation is then passed through a component that disperses that wavelengths. So here, if that heated gas, the light from that gas is passed through a prism, the light will get dispersed and we can see the component wavelengths coming from the heated hydrogen gas. So if you observe the screen here, we can see that you get a red line, a green line, a blue line and two violet lines. So only these wavelengths are being shown from this gas. That is, only these particular energy levels are available in hydrogen gas. Okay, so if we heat hydrogen gas, it can be excited only up to specific energy levels. And by the de-excitation of this gas, with this gas, if it is taken out, it will start to cool, right? So light will emit from it. And if we study that emission lines, we can see that the light will come from only these particular energy levels. So red light means E is equal to H nu. Nu is larger, right? So it will be equivalent to the molecules that is de-excited from higher energy levels to ground state. Now this red line represents that its wavelength is in the higher order. In terms of frequency will be low, right? So in the energy level spectrum, I can see that E is equal to H into nu frequency. So that means the atoms in the lower first or second energy levels, they are de-excited to the ground level. And that de-excitations, those emissions are represented by the red line. Now the violet line represents de-excitations from higher energy levels, because violet has lower wavelengths. It means it has higher frequencies, and that means it has higher energies. So the atoms are de-excited from higher energy levels. Now different elements have different emission spectra. This spectrum is a fingerprint for different elements. So in hydrogen, we can see that its emission spectra has a red line, a green line, a blue line, and several violet lines. For sodium spectrum, emission spectrum, it has a characteristic two yellow lines, yellow 1 and yellow 2. Likewise, for helium, neon, and mercury. So emission spectrum is a type of fingerprint for each element, each gas. It can be used to identify which gas is present there by studying if we have an unknown gas mixture, if we study the emission spectrum from that unknown mixture, we can say that by studying the emission spectrum, we can identify which type of gas is in that. Now, in absorption spectroscopy, we take a cool gas and pass light through it. So we have a source light, a hot bulb here. It is placed in front of a cool gas. This is our sample. And then the light will be passed through the gas. The light will pass again through a slit into the prism. and the prism will show the component colors that are coming through it. Now here what happens is, when this hot bulb is shined upon this gas, this hot bulb is a continuous spectrum. It has almost all the wavelengths. So when this is passed through the cool gas, the gas gets heated up. That is, it is getting excited. It is excited by absorbing particular wavelengths. Okay, that gas will absorb only particular wavelengths, only its characteristic wavelengths to get excited. So the gas will absorb those wavelengths and the remaining light will pass through. And this light, when it is dispersed and it is seen on a screen, in this spectrum we can see certain gaps, certain lines that are missing. So we understand that these wavelengths are absorbed by this sample gas. And this spectrum is called the absorption spectrum. So here the atoms of the gas will absorb those particular frequencies. This is the absorption spectrum of the sun. So the sun is giving us a almost wide continuous spectrum, but in that, if we study in closely, we see that there are a lot of gaps, a lot of spectral wavelengths that are missing. So we understand that these particular wavelengths are showing the presence of gases in sun. And by studying the missing wavelengths, we came to understand that there is hydrogen, helium, neon gases in a larger fraction in the atmosphere of the sun, in the chromosphere of sun. The sun itself is a huge ball of gases, right? So by studying the spectrum from the sun, we get to understand what are the component gases in the sun. Well, this picture is shown just to differentiate between a molecular spectra and an atomic spectrum. So let us consider hydrogen. In hydrogen, uh, we are taking excited atomic hydrogen and excited molecular hydrogen. Molecular hydrogen means two hydrogen atoms are bonded. Now, the picture A shows the spectra from molecular hydrogen, whereas picture B shows the spectra from atomic hydrogen. You can see the difference between these two spectra, right? In atomic hydrogen, there are only a few spectral lines, its characteristic fingerprints. Whereas in molecular hydrogen, there are a lot of spectral lines. Okay. Now, this picture shows the electromagnetic spectrum. Electromagnetic spectrum is a very broad range of wavelengths, ranging from cosmic rays, gamma rays, X-rays, ultraviolet rays, visible light, infrared rays, microwaves, and radio waves. In that, what we see comes only in the visible light range. Okay, that has a spectrum of Vibgyor colors. This electromagnetic spectrum, it is consisting of waves, and we signify a wave uh, by representing its frequency or its wavelength or its energy. Now the frequency is always expressed in hertz. Its unit is 1/second. Wavelength is expressed in different units. It is actually the distance traveled for a complete cycle, and angstrom is common for shorter wavelengths like gamma rays and X-rays up to UV rays, whereas nanometer is common for ultraviolet visible spectrum, which is used for microwave spectroscopy. Now, energies are expressed in different units. One such unit is electron volt. In particularly for atomic spectroscopy, photoelectron spectroscopy, and mass spectroscopy, we use the unit electron volt. And 1 electron volt is defined as energy that an electron acquires after passing through a voltage difference of 1 volt. So when an electron passes through a space of 1 volt difference, it will have acquired 1 electron volt. There are other units, and commonly in spectroscopy, wave numbers are used to represent the energies of the radiation, and that is 1 by wavelength, 1 by lambda. Energy, it is represented in h nu, where nu frequency is equal to c by lambda. It implies energy is equal to hc by lambda. So in hc by lambda, we have the unit of wave number. Now let us look into the electromagnetic spectrum. This spectrum ranges from 3 into 10 raised to 7 hertz to 3 into 10 raised to 20 hertz. It can be in the order of increasing frequency from left to right, or in the order of decreasing wavelengths from left to right. So in this I can say that in the left area we have the radio waves, microwaves, and then moving towards the right I have the infrared waves, the visible light, then UV rays, again towards the longer frequency side or shorter wavelength side we have the X-rays and gamma rays. All these rays, these radiations, they pass through the Earth's atmosphere. But the Earth's atmosphere is transparent only for radio waves and visible light and infrared rays. So these two windows, it is showing that the atmosphere is opaque for all other radiations and it is transparent only for the visible light, infrared and radio waves. Here, in certain regions, we can see that there is overlapping of these spectral regions. That is, here the ultraviolet far region is overlapping over the soft X-rays, whereas the hard X-rays are overlapping over the gamma rays. And in general, we have designated the electromagnetic spectrum into 6 different regions. Now the first is the radio frequency region. Its frequency ranges from 3 into 10 raised to 7 Hertz to 3 into 10 raised to 10 Hertz. In this region, we see nuclear magnetic resonance at the lower frequency range and electron spin resonance at the upper radio frequency range. Now let us look into nuclear magnetic resonance in the lower radio frequency range. Consider the nucleus as a point charge spinning about its own axis. Now, since the nucleus is positively charged, so you have positive charge that is moving around and it implies a circular current. Now, a circular current will form a magnetic dipole. Thus, the nucleus is equivalent, it is identical to a tiny bar magnet that is suspended along the spin axis. Now, when this nucleus is subjected to external magnetic field, that is when radiation is falling on this nucleus, radiation is having electromagnetic components. Radiation is EM wave, right? So, when EM wave falls on nucleus, the direction of the spin of the nucleus can change. If this was the initial direction of the spin of the nucleus, it can change. And this change is seen as the nuclear magnetic resonance phenomenon. This change shows emissions or absorptions in the lower radio frequency range, that is 100 megahertz, that is 10 raised to 7 hertz. Now the energy change involved can be calculated as E is equal to h nu. energy h nu can be written as h Planck's constant 6.626 into 10 raised to minus 34 into frequency, that is 100 megahertz, 100 into 10 raised to 6. This is given as 6.626 into 10 raised to minus 26 joules. This is a very small value. We won't be able to measure it. Hence, we consider the energy for 1 mole. Okay, that is for Avogadro number of molecules, we calculate the energy. Now multiplying this with the Avogadro number 6.02 into 10 raised to 23, we get 3.99 into 10 raised to minus 2 joule per mole. This energy can be measured using instruments. And this is the energy change involved in nuclear magnetic resonance. Now let us look into electron spin resonance. In an atom, the electron is a charged particle and these electrons are moving about its orbital. Hence, this also constitutes a circular current and it forms a magnetic dipole. Again, when light is falling upon these electrons, its spin can change and this leads to electron spin resonance. This happens at the higher radio frequency range of 10 raised to 10 hertz. And the energy change here involved, if it is measured for just one molecule, it will be of the order of 10 raised to minus 24 joule. Again, very small. Hence, we measure it for one mole, that is Avogadro number of molecules. Hence, energy change involved will be measured as 3.99 joule per mole. That can be measured in instruments. Now, the next region in the electromagnetic spectrum is the microwave region. The frequencies in this region range from 3 into 10 raised to 10 hertz to 3 into 10 raised to 12 hertz. Now, this will deal with rotating molecules and hence this region of spectroscopy is called rotational spectroscopy. And the energy change involved here is 10 raised to 2 joule per mole. You can calculate it using NH nu. Now, polar molecules like water, carbon dioxide, HCl and NH3, they have positive and negative center of masses that do not coincide. So in this picture, if you look at, in this HCl molecule, the positive center and the negative center, they do not coincide. Again here, the negative center is of nitrogen and the positive center of these hydrogens, they do not coincide. The positive center will be along here, negative center will be here. Again, in CH3Cl molecule, this four molecules, they have the positive center, it will be nearer to this region, whereas chlorine will have the negative center, it will be nearer to this region. So these positive and negative centers are not coinciding, they are separated, hence they form dipoles. So rotation of these molecules implies the positive and negative centers to change places periodically. So when the molecule is rotating, these positive and negative centers, they continuously change. And this fluctuation of this dipole gives rise to rotational spectrum. It is explained in this figure. So we said that these polar molecules, they are represented by a dipole. And when they rotate, like when these molecules are excited and if they happen to rotate, if they are rotating, the direction of the dipole will continuously change, right? We see the dipole rotating here. Okay, first it was like this, then it rotated, then it rotated, rotated. In all these cases, the direction of the dipole is changing. When its direction changes, we see that its energy, the energy of the dipole is also changing. That dipole is, it can rotate by either absorbing energy or it can rotate by either emitting energy. So in these two cases, we can take energy measurements from it. And this energy will be in the range of microwave region. So we get energy only in, like rotational energies, only from polar molecules, only from molecules with permanent electric dipoles. So polar molecules are microwave active, whereas non-polar molecules are microwave inactive. Now the next region of electromagnetic spectrum is the infrared region. Here frequency ranges from 3 into 10 raised to 12 Hertz to 3 into 10 raised to 14 Hertz. And this deals with vibrating molecules. And hence this region of spectroscopy is called vibrational spectroscopy or infrared spectroscopy. The energy range, the energy change involved is at the order of 10 raised to 4 joule per mole. And here the energies are produced due to vibration of the molecule. The molecule can vibrate in three types. It can show symmetric stretching vibration, it can show asymmetric stretching vibration, or it can show bending vibration. So in this slide, we can see here in the top right corner, the molecule carbon dioxide is exhibiting the three different types of vibrations. The first one, symmetrical stretch, the positive and the negative centers will coincide at C itself. Even though if it is stretching, since the stretch is symmetrical, the negative center will coincide with the positive center. In bending vibration, since the negative and the positive centers do not coincide, it will show a change in the dipole moment, and hence it can be seen as a radiation from the molecule. Likewise, in asymmetrical stretch, we see that the positive and negative center is not coinciding because of the asymmetry in the stretch. Hence, it will show a difference in the dipole moment and show energy radiation from it. So in the symmetric stretching vibration, when the bonds in the molecule are identically stretched or compressed, the dipole moment remains zero. And since there is no change in the dipole moment, this vibration is infrared inactive. Whereas in both in asymmetric and bending vibrations, the dipole moment change is observed, and hence they are infrared active. This picture shows the asymmetric stretching vibration. We see that the negative center is not coinciding with the positive center. Hence, there is a dipole moment change, and this change is shown as a radiation from that molecule. Now the next region is visible and ultraviolet region. Its frequencies range from 3 into 10 raised to 14 Hertz to 3 into 10 raised to 16 Hertz. Now here we can see these radiations because valence electrons in the atom jump from one energy level to the next higher or lower energy levels, and this gives emission or absorption spectrum. And this region of spectroscopy is called electronic spectroscopy. The energy change involved here is the order of 10 raised to 5 joule per mole. The next region of study is the X-ray region. Here frequency ranges from 3 into 10 raised to 16 Hertz to 3 into 10 raised to 18 Hertz. Now when an electron strikes a target, that electron interacts with the atoms of the target in two different ways. First one is when the electron is interacting with that strong electric field of the atomic nucleus, when this electron is coming nearby this nucleus, it is decelerated due to this nucleus. The slowing down causes energy to be radiated from this electron. And this is called Bremsstrahlung. These radiations that is emitted are called continuous X-rays or Bremsstrahlung X-rays. Now, the second type, one high energy electron, while it comes near the nucleus, it may collide with one of the inner K shell electrons and knock it off. Okay, so when this high energy electron is striking this particular inner K shell electron, it will remove it from its location and make a vacancy here. So this electron then will move away. This K shell electron will be knocked off as a photoelectron, and there is a vacancy left here, right? So the electrons, these atom, it needs to stay in the most stable state, stable energy levels. So if there is a vacancy in the inner energy levels, it will be unstable. So electrons from the higher energy levels will fall into the lower vacancy in the lower energy level. And when they fall into it, they will emit radiation. That is called the characteristic X-rays. Characteristic X-rays are the fingerprint of that particular target element. Now this will be the broad X-ray spectrum that we get from that molecule. Here this broad range is the continuous X-rays or Bremsstrahlung X-rays, whereas these spikes are the characteristic X-rays. The energy change involved here is of the order of 10 raised to 7 joule per mole. Now the next and the last region of the electromagnetic spectrum is the gamma ray region. Here the frequency ranges from 3 into 10 power 18 Hertz to 3 into 10 power 20 Hertz. The gamma rays here are emitted due to rearrangement of nuclear particles. That is, if the parent molecule or parent atom is excited, its nuclear state is also getting excited here due to gamma radiation. Then when it is de-exciting, this nucleus will come back to the stable state by emitting a gamma ray. Then we are studying these gamma rays. This study is called gamma ray spectroscopy, and the energy change involved here is of the order of 10 raised to 9 to 10 raised to 11 joule per mole. Now, let us look into how we shall study, or what is the device that is used to study the radiations. In particular, how is the working mechanism of a grating spectrometer. So in this grating spectrometer, we have different components. We have a source light, and the source light will fall into the telescope, and the light from the telescope is passed through a slit. The slit will try to reduce the range of frequencies that is passing into that instrument. The slit then, light passing through the slit will fall onto this plano-concave mirror, and by virtue of its design, this mirror makes the incident light into parallel beam of light. This parallel beam of light then falls on a diffraction grating. The grating, what it does is it separates that light into its component colors. So these component wavelengths are produced by the diffracting element. By rotating the grating, I can select which wavelength to fall on this mirror. Okay, so wavelength tuning is produced by rotation of the grating. Now this mirror then, it focuses the light incident wavelength upon a detector, and that output can be recorded into a computer or onto a graph. So the radiation is from a source, a hot or incandescent filament, a white light source, so that there is all wavelength all wavelengths from it. And on rotating the grating, a series of frequencies can be tuned across this mirror. Now the detector may be a thermocouple. Thermocouple means it can measure heatness. For infrared radiation, we'll be able to measure the heatness. Or the detector may be a photomultiplier tube. That is, it can measure the light for visible and ultraviolet radiation. What happens in the detector is it converts this EM wave into an electrical signal. Light is converted into an electrical signal. And this electrical signal is recorded immediately into the computer. Here, what we need to understand is the slit, it shows a sharply defined image. So if the slit, by the nature of the slit, the shape of the slit, we get a sharply defined image. And if we use a very narrow slit, we get a smaller frequency range to pass through. Now we use narrow slits to prevent stray radiations from falling into the instrument. Another thing is that the sample that needs to be studied, it is placed nearer to the slit, because if it is nearer to the slit, the radiation will pass through all of that sample. The radiation is focused into that sample. So it is placed close to the slits to minimize its size. Only a small sample needs to be taken there. It is preferably placed near the exit slit, where it is bathed in a narrow range of frequencies. If the sample is kept here, all the frequencies are falling into that sample. Whereas if the sample is placed at the exit slit, only particular frequencies will be falling at a time, since we are tuning it using the grating. Okay, so placing it near the exit slit is preferred. Now, let us see how we take a recording of a spectrum from this spectrometer. We can take a recording in two ways, either in time domain spectrum or in frequency domain spectrum. In time domain spectrum, the detector output is recorded against time. That is in this figure we can see that for each 0.01 seconds, the spectrum is recorded. So here I can see a series of frequencies. These frequencies, this wave, this electrical signal, is a composition of different frequencies. So this is a composite signal that I am getting. And this composite signal is measured against time. In 1 second, 2 seconds, 3 seconds, it is measured continuously in time. Whereas in the frequency domain spectrum, the output is recorded against frequency. That is, this lower graph shows the frequency domain spectrum. And here I can see that what all frequencies are present at that time is measured. So at this instant, I'm not seeing that complete wave. I'm only seeing the frequencies that are available in the output at that particular point. Usually we take spectrums in the frequency domain spectrum. Now in this picture, I can show the difference between these two domains. So if we have different wavelengths passing through the detector at a particular instant, I have the green wavelength and the violet wavelength passing through the detector. The time domain spectroscopy, I get the sum of these two wavelengths in the output. Whereas I get the particular green and violet wavelength only in the frequency domain output. Now, ideally, we would expect an output as shown in the top picture. In the frequency domain spectrum, we should be able to see only that particular spectral line, that particular wavelength in the output. But in practice, it is not so. In practice, we see the spectrum as shown in the bottom picture. This is because the source may not be able to emit a single wavelength. If we are using a monochromatic source light, even if we say it is a monochromatic source light, it will not be able to produce a wavelength particularly of 1 nanometer. It will be producing light in a range of wavelengths. It may be ranging from 30 nanometers. The frequency range may be of 30 nanometers, or it may be of 100 nanometers. Hence, that spike, that output will have a range. The width of this that peak will be accordingly 30 nanometers or 100 nanometers. Okay. Now, so source sensitivity is one factor. Now, the detector sensitivity is also another factor. The detector is also frequency dependent. Like if we think of our eyes can see green and yellow light better than the red and violet lights. Okay, our sensitivity is more for green and yellow. Likewise, our instrument detector, its sensitivity is also different for different frequencies. Hence, that will lead to the broadening of the spectral line. Another factor is that it is impossible to make slits infinitely narrow to pass a single frequency. So in this earlier figure, we said that by using a slit, I can narrow the range of frequencies falling onto that grating and then falling onto that detector. But I cannot make the slit size infinitely narrow. I have a difficulty to make it infinitely narrow. I can make it narrow only up to a nanometer dimension. And hence, this will create a finite thickness in the spectral width. Another point is that energy transitions in atoms or molecules are not sharp. Like if I am exciting an atom from the ground state to the first excited energy level, this ground state energy level is not very sharp. It is not a single energy. It can be a band of energy. So the lower energy band can be the atom can be excited from the lower energy band to the higher energy band. So when I speak of bands, the atom can be excited from the top of the lower band to the bottom of the upper band, or it can be excited from the bottom of the lower band to the bottom of the upper band. Okay, so even if I say energy is quantized, it is fixed, there is a small broadening of these energies, and since these transitions are not sharp, there is a spectral broadening here. Another factor in the spectrum that we do not want is the electrical noise in the spectrum. Here we see different small amplitudes of wavelengths that has come up. This is due to the electrical noises in that instrument. Now, in order to understand or get the perfect data from this spectrum, what we do is that the top part, this is the actual spectral trace that we get from the instrument. But to identify the position of the peak, exact position of the peak, or to measure the half width of this peak, half width means by measuring the width of this peak at half of its amplitude. So to measure that, we take the derivative of the spectral trace, the derivative of this spectrum. Now, derivative implies that at the peak, the rate of change will be 0. At the increasing side, the derivative will be maximum. At the decreasing side, the derivative will be minimum. Right? So by taking the derivative, I can exactly locate the center of the peak. I can exactly measure the half width maximum by taking the distance between these two peaks. Between these two peaks, I can measure the width. Hence, for instrumental reading, for better measurements of relative intensities of these absorption or emissions, we take the derivative of the spectral trace. That's all for today's session. Thank you.